Hello friends, welcome back. We're going to be discussing graphs now. Graphs are another non-linear data structure or abstract data type that we can use to represent information. A tree actually could be considered a generalization or, well, a more specific graph, and a graph could be seen as a generalization of trees because you can have graphs that aren't trees, but all trees are technically graphs. They're just acyclic, meaning none of them have cycles in them. So we will learn a lot of terminology related to graphs, and then we will also learn an algorithm that I was quite shocked was not really mentioned or explicitly explained in the book, which was a little bit bizarre because it's like the most popular algorithm and it's used in networking, called Dijkstra's algorithm. Dijkstra, so Dijkstra, Dijkstra's algorithm. So we will do an example of that. I actually already have another working example on my YouTube that you can go through, but I will do another one for this lecture for you guys alone. So you're very special. Now, roadmaps could be an example of a graph. So each of the cities could be considered a node through the roadmap, and the paths between them could be seen as edges on the graph. So a graph, definition of a graph, is a collection of distinct vertices or nodes and distinct edges. So just like we have edges between the nodes in a tree, we typically for a graph you call them vertices, but nodes is a perfectly fine name for them. A subgraph is a portion of a graph that is itself a graph. So again, we have that recursive structure. Here's an example. This is a directed graph, or a digraph, D-I-G-R-A-P-H, digraph. So if you ever see digraph in the literature, you'll know it's just short for directed graph. In some cases, with a directed graph, we would need to indicate when there is direction. So this would, for example, be a two-way street, but then some of these streets or paths are one-way. So you can only go from this node to this node, but you cannot go in the reverse direction because the arrows are pointing. And then some are undirected graphs where you would just see a line connecting the nodes, and the assumption is you can go in either direction. A path. So we need to formalize what's a path. A path between two vertices in a graph, so any two vertices in this graph or any other graph, so this one and that one or this one and that one. A path is a sequence of edges. A path in a directed graph must consider the direction of the edges, that's called a directed path. The length of the path is the number of edges that it comprises. And a cycle is a path that begins and ends at the same vertex. So if you only repeat the one vertex twice and you go in some sort of a circle, essentially that's a cycle. It's a path from the node back to itself. So if I went from Barnstable back to itself through Orleans, so Barnstable to Orleans, Chatham, Hyannis, and back to Barnstable, I want to say this is in Rhode Island or New Jersey or something. I don't know. It looks, some of these names are very, very British, and they match the names of British cities. So I'm assuming that this is something in New England. So weighted graphs. So besides being either directed or undirected, you can also have weighted and unweighted graphs. And weighted graphs will play a specific role when we discuss Dijkstra's algorithm. So a weighted graph has values on the edges. The values are called the weights or the costs. Now they could represent a good thing. So they could represent something that's increasing as you collect them and go across the paths. But in this case, if you look at it, it would probably indicate like number of miles or kilometers or something between the different towns if you take that path. So that would be a weight or a cost. So something we might want to do, in other words, a classic algorithm or classic problem that we want to solve and come up with an algorithm for that problem, would be shortest path. So coming up with the shortest path. It would be, now, does that necessarily mean miles? No. Let's assume, if this were like just a map of the United States going from, say, New York to Los Angeles, if you have one that takes kind of a longer path in terms of miles, but is cheaper in terms of how much it costs, you might decide that that one, the cost is the one that you're going to pay attention to, so you would consider that the weights on the graph and not the mileage. Or you could take both into consideration, but that starts getting very complicated, and then you get into what's called multi-objective or many-objective analysis. So connected graphs, a graph that has a path between every pair of distinct vertices is considered connected. So if they're disconnected, that means you have separate subgraphs that you can't get from one node to every other node. If you can get from a node to every other node in the graph, it is considered a connected graph. A complete graph, so just like we have complete trees, we can have complete graphs. But for graphs, a complete graph has an edge between every pair of distinct vertices. Undirected graphs can be connected, complete, or disconnected. So here's an example. This is a connected graph. It means that you can have a path from A to B. Complete means every node is connected to every other node. So this one's connected to all the other three, and then this one's connected to all the other three, this one, and this one. So every node's connected to every other node. And then disconnected, this would be one graph right here, and we would consider this a subgraph, but it's a node unto itself. Or it may be connected to another node. That would be fine as well. Now, there are implications with these. This is not just, fun math theory or something that people just like thinking about, although there are pure mathematicians or people that study math for math's sake that do study graph theory very heavily just for the sake of it, but there are a lot of applications in graph theory. It comes down to circuit design. So if you're going into computer engineering or electrical engineering, circuit design does involve graph theory. Data science is very heavily involves graph theory in certain circumstances, like social networking analysis and things like that, and also just general networks, regular networks where you have routers connected or end hosts. For example, this might be a person trying to communicate with another person, or rather two machines, and it has to go through all these routers on a network. So what do we consider what would we consider the cheapest path or the shortest or simplest path? And the routers have to decide this. What if a router in the graph goes down? Router in the network goes down. How do you figure a way around it? Is there a way from this node to that node? Say a node in New York to a node in Los Angeles, how does it decide how to route traffic? So a lot of this has to do with certain algorithms, such as Dijkstra's algorithm. You get when you start talking about distance vector and linked state algorithms in networking, then you do start using graph algorithms quite a bit. And actually, one of the biggest names in graph theory, I think he's still alive. I think his name is Gary Chartrand. Gary, I always get his first name wrong. Gary Chartrand. Yeah, he's still alive. I believe he is retired now. I want to say he's retired now. But you'll notice he actually graduated Michigan State. I won't hold that against him. He's still very smart. But he got his degrees from Michigan State, and also he taught at Worcester, Michigan for many, many years. He's professor emeritus, which means he's retired. But he's given an honorary title, even in retirement, that he can still use the title professor. He advised 22 doctoral students in the research areas of graph theory, and actually one of them, I forget the guy's name, but he's a professor that actually does a ton of graph theory stuff at U of M Dearborn. And so he's written several books, but he's known for a lot of books. There's one book from Dover that's just on graph theory. Let's see if I can find it. It might be that. Graph theory. Nope, that's Rich Trudeau. That's not graph. We'll say graph theory. Graph theory. Sorry, graph theory. And we will do Chartrand. And this one, yeah, that right there. So that's a Dover book and those are usually very heady. As far as this book is concerned, it's an older book, but it's actually quite applicable, and it's actually really good. It has 320 pages just on the topic of graph theory, so that should give you an idea that, and that's a rather small book, so that should give you an idea that there's a lot to discuss as far as graphs are concerned, and it has a lot to do with if you're delivering a package or if your GPS is trying to figure out where you're going and what the shortest path or the best path is, can it do that in a reasonable amount of time, etc., etc. A lot of that has to do with graphs. So I hope I've convinced you graphs are important. Other terminology. So we've got the terms nodes or vertices. Those are the same thing. And then edges. An adjacent vertex. Vertices are adjacent in an undirected graph if they're joined by an edge at all. But in a directed graph, we would say that if you have an incoming edge, you are adjacent to the node from which you were coming in. So vertex A is adjacent to B, but B is not adjacent to A. So if you can get to A from B, then we say A is adjacent to B. Airline routes, another set of graphs here. So these are different airline routes right there. Here, this would be Florida, of course. And then if we can get from one place to another, you might have to decide based on weighting or something like that, is there a shorter path, one way or the other. Mazes, we might look at this and say, well, I don't know how to represent that as a graph. How would we do that? Well, you can actually say, well, there's a starting node. There would be a node at every intersection and every dead end. So you would look around here and then create these nodes, which you could create here. So finding the path from here to there would be a problem that you could solve using graph theory. This is important, and this will very likely be on your exam, your test for the end. So I would recommend you learn this very, very quickly. It is a course prerequisite. You could show this as a topological sort or a topological ordering. You look at these and the way you do the sort, and they aren't unique, meaning there could be more than one order you could come up with. But we see at this case, no matter what, all of our orders are going to start with CS1 because you can't, for example, take Computer Science 2 without having Computer Science 1. So the order has to be CS1. Then you would basically erase this and just list it as CS1, and then erase the arrow and then say, okay, what now has no incoming arrows? And then you would see CS2 doesn't. You erase that, and all of its outgoing arrows go away. So we've got CS1, CS2. Then I get to pick. I can do CS3, CS4, or CS5. Usually we resolve ties by going with the lower numbers or alphabetically, etc. And then you obviously also don't want to have any kind of cycle in these graphs. So these graphs should be acyclic. They should not have a cycle. For example, if CS4 was a prereq to CS7, which is a prereq to 8, if that was a prereq to 6, which was a prereq to 4, you'd have a cycle here, which means you could never actually take any of the courses because you'd be waiting to take the other course. Because I can't take this one because this one's a prereq, but I can't take that one without this one without that one, and that one without, oh, that's where I started. So that would be a really bad situation. My brother has a friend that he's was in a band with, who has a master's degree in I believe brass performance, so basically trumpets and things like that, and he's taught music theory for years at Eastern, and he went back to study for an education degree because he wanted to teach in K through 12. Now the thing most people don't know is to teach in college you don't need an education or a teacher's degree or a certificate. It's assumed you're teaching a set of adults and you're teaching them a lot of times applied skills. Whereas they need to teach K through 12 or kindergarten through 12th grade, you need different levels of adolescent psychology and stuff like that. I took courses like that in college, but it wasn't because I wanted a teaching certificate. But most people don't. Most people that teach in these areas don't. So anyway, he had to ironically go back, even though he had a master's degree in trumpet performance, to teach music at the K through 12 level, and they when he was going to Eastern, because he, as an adjunct there, he actually got discounts or got to take courses for free there. So he meant to take they made him take all the courses that he would be really good at, including like beginning music theory, which is funny because he teaches the course. And ironically, he was actually signed up for the course that he was scheduled to teach. So he asked the department chair if he could give himself an A. So I thought that was kind of funny. So it's kind of a cyclic situation, right? Traversals, you can have depth first and breadth first. I won't hold you super responsible for these, but just to give you an idea, depth first is you go as deep into the graph as you can. So I go from here to 2 to 3 to 4, back up only when I have to, and then go forward, keep burrowing forward as much as possible. Then you go back, go as deep as possible, then go as deep as possible, right, and then as deep as possible. Breadth first is a little more cautious. So you would start here. If you think about the story, I don't know if you've ever heard of it, but the story of, I believe it's Perseus and the Minotaur, where he basically he doesn't want to get lost in this huge thing called the labyrinth, and there's also a big ugly monster in there called the Minotaur. So he wants to keep track of, even if he slays the Minotaur, he doesn't want to die because he gets stuck in the labyrinth. So he ties a string and then paints every time he gets to a specific hallway or takes a particular passage, so he knows if he's been there or not. So this is kind of like unraveling the string, painting it, saying okay, and then coming back, unraveling, and then being very cautious. So this is breadth first. So you try to go not deep, but as wide as possible into the caverns or whatever. Now I know this looks like a tree, and these both look like trees, because really they are representative of the same graph, but the graph may very well have edges that connect back and such, but it's not always the case that you're going to, when we say there's a traversal, we look at the traversal as a tree. So you can look at the going into the graph as a tree. So then they show you some of the code samples and such. Depth first, but again, you're not allowed. You're not responsible for that. So, topological order, mentioned it before. This is the prerequisite chart. Definitely don't want any kind of cycles in this, and you do need this for your test. You need this for your test. I'm going to say it again. You need this for the test. It'll be take home, obviously, but you'll need it. Yeah, we definitely don't want to cycle. So if I took CS 15, that was a prereq for 20. And then it comes back like this. That's not good. Okay. See if there's anything else. I think we're pretty good on this. I think they look at shortest paths, but they don't really go over the algorithm very well, at least. So we're going to... I guess Java interfaces. They do have interfaces available for the graph. You can create some in Java. Those are ones that you create yourself, and what we're going to do, we're not going to go over graph implementations, but what we're going to do is I'm going to do an example. Let me double check at what time we're at. That's still good. Okay, so we're going to do an example. I'm going to get my little drawing pad here. Hope it doesn't go super sensitive on me again. We're going to maybe use red here, and I'm going to make the thickness a little bit better. So let's see if that's good. That's pretty decent. Now, this is how Dijkstra's algorithm works. Dijkstra's algorithm looks at a graph, and it's a weighted graph, and the idea is to find the shortest path. The name of the full algorithm, most people just say Dijkstra's algorithm, but the name of the full algorithm is Dijkstra's single source. So single source, so Dijkstra's single source shortest path algorithm. Path, okay. And we need to be careful. I guess one thing to mention is that Dijkstra, he passed away, I think, in 2001. So a lot of us, that's within our lifetimes. So he's not like from the 1700s. This algorithm was determined by someone very recent, or relatively recent. So this algorithm is called the single source algorithm because it finds the shortest path given a single source. So if I tell you the source is A, or the source is B, or the source is E, the values that you get in the final table that we will determine could be different, will be different in many cases. So I'm going to tell you that A is the single source, and here's how we initialize our table. You're always going to have vertex with the list of the vertices, whether they're letters or symbols or numbers or what have you, whether it is, quote, known or not. This is very similar to visited on the tree traversals. So known as like the tree traversals. So we basically say, have we, quote, officially visited it yet? And marked it as known. And once you mark it as known with this algorithm, you're claiming that you know now the single source shortest path, both its distance and how to get there, back to the single source. So, and then you say the distance, and then you also say where did you come from to get to that. So since A is going to be our single source right here, I'm going to mark that and say that it is known, but I'm going to initialize the others to false. Okay. This is going to take some fancy erasing, just letting you know. And then the distance, we don't assume a distance or a previous, but we assume the distance is infinity in all the others, so because we don't know yet. And now what you do, the algorithm's actually fairly simple. You only look to what's connected to the node under consideration. So I want to know, okay, what is the shortest path so far from A to B? So A is connected to B, and A is connected to C. So I would say what's currently in the table and is the value I'm looking at, total distance to the single source, shorter than what's in the table. And since these are directly connected to the single source A, I can confidently say that the infinity I have here is definitely larger than the 15 that I have there. So what I'm going to do is, I know this is going to screw up the colors, but I'm going to get rid of the infinity there, and I'm going to put a 15. So there's a 15 there now, and that's if I come directly from A. Now the other one, right here, C, I know that the 6 that's connecting my C to my A directly is definitely smaller. So I'm going to write a 6 right there. Very good. Now the algorithm continues. Since I've exhausted all of the nodes connected with A, which was the node under consideration, and notice I did not mark anything known yet, but I do need to next pick another node. I go with the shortest path of any node, or the shortest distance of any node that is not marked as true. So I look at all the falses, which is all the other nodes besides A so far, and I look for the shortest or smallest number. And that happens to be C. So C is the second notice that I officially visit. I'm going to put that as a true, and then I know that the 6 is going to be the smallest I ever get to. So that's, and that's coming from A. So I now look at C, and I mark it because it is known. And I look at the nodes that are connected to C. I have B, D, and E. I don't look back at A because A is already marked as known. But B, even though we've seen it before, it is not marked as known. So I can reconsider B. So I have to look at B and I ask, is the distance from A, if I go through C, shorter than the one that's already in the table? And since C to B is 6, and from A to C, right, is already a 6, so you add it to the value here. The 6 between these plus the 6 here is 12, and 12 is in fact shorter than 15. So I'm going to correct this, and I also have to update where did I come from directly, because I'm no longer coming directly from A. I'm now actually going through C. So I have a 12 right here, and then I'm going through C. So just because the B was connected to the A to start with does not mean that that was the shortest path. So now I continue. So I've got B updated. Now what about D? Is 6, 7, 8 shorter than infinity? In fact it is. So I'm going to put an 8 there, going to put an 8 there, and we are going to say that is if I directly come from C. Now I look at what else C is connected to. It's connected to E, and the 6 that's currently already there plus the 3 is 9 to get to E. So I'm going to erase that, and then I'm going to put that is a 9 if I take it through C, and that's the only other thing that C is connected to. I continue with the algorithm. I look at the ones that are still labeled as false, F, 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 and I look for the one that has the smallest distance from the single source. That node happens, the C is already marked true, so we ignore that. So 8 is the shortest. 8, 9, infinity, and 12 are the 4 F's left, the falses. Okay, true and false here. The falses are 12, 8, 9, and infinity, and 8 is clearly the shortest, so D gets to be marked as the next known. Okay, so I'm going to take D here, and I'm going to update this to true, and we know the shortest path now to D. So now let's look at D. D does look at its connection with B, and D has 8, and then 4 more is 8, 9, 10, 11, 12. We look that B already has 12, and that doesn't improve it. So if it ties and it does not improve it, we don't update it. If it were to say 11, we would update this and say, oh yeah, B comes from D. But since it didn't improve it, it wouldn't matter, so we don't update it. That's how the algorithm works. The only other thing that D is connected to is C, which is already visited, and then F. So F is infinity, and if we add that 1 to the connection between D and F to the 8 here, that becomes 9. So I'm going to erase that, and we're going to make that a 9 to get to F coming through D. So now I've got 3 things marked true, 3 things marked false, and we look at the ones that are still false, a 12, a 9, and a 9. And since there's a tie here for shortest, we go with the one that's alphabetically or lexicographically smaller. So we'll go with E, but truth be told, it wouldn't really matter at this point. I'm just going to mark this E here. I'm going to mark E as true, and we will assume that it is, we know the shortest path to E. It goes through C, and it is a 9. Now we look at E, and it is connected to C and F. The only one of these that is still marked false is the F. So we say E's distance is 9, 10, 11 to get to F. F's is already at 9, 11 is not smaller than F, or smaller than 9, so we leave it alone. We do not update it. So we're done with E. Now we look at the 2 remaining falses. The 9 here is the F. We erase that and mark it as visited or known. So we say that's true, and we mark it here. And you'll notice it's not connected to anything that isn't already known. And then we're left with B, poor little B here. Also, we just mark it as known, and we say that's true, and it's not connected to anything because we know all the other. It's not connected to anything that isn't known already as the shortest path. So now we have our table of shortest distances. So if you're asked a question, I could ask questions like, say on a test or something, what is the shortest path from the single source to D? Or what's the length of the shortest path of the distance? You would say, immediately you could just say A. 8 is from A to D. What if I said from the shortest path, the single shortest path distance from A to F? You would know that the distance is 9. Now, if I asked you what the actual path was that you would take in the in here, it's actually quite simple. So if I say from A to F, I want you to give me the actual path. So I start with the F right here, the F, and it came from D, right? So you write this backwards. It came from D. D came from C, and then C came from A. So you write that in reverse, and I've got the shortest path from A to F now. Very simple. What about from A to D? Well, if I look at D, D came from C, so I write that, and then C came from A, and then A is our single source. So that's exactly what I wanted. So that's all. You just have to be able to run the algorithm and answer questions about distances and also the actual paths. Okay, I would highly recommend going through the algorithm and not trying to eyeball it, or you will end up with a bad solution. So that's it for this lecture, and this is essentially the final lecture. I will be posting the final project information, final exam information soon, so that you can do it at your leisure. But please make sure you are prepared. I will try to let you know what will be on the test and how we're going to do that also soon. So thank you, and I will see you soon.